2019, we actually launched the first satellite for Nepal called NEPALISAT-1. And as you will see here, the Honorable Prime Minister KB Sharma Oli, mentioned that Nepal had entered into space era. I would say it's still not as entering as into space era as he was thinking, but it's still a significant step towards that direction. So by launching a satellite that was about a kilo, Nepal had sort of formally entered the space era. So what does actually space mean? I think that's a question that we need to explore first. So space, the formal definition for space is basically any line that crosses the Kármán line, which is about 100 kilometers above the surface of the Earth. That's considered as space. Anything that is launched above it is a spacecraft, okay? So the Kármán line is about 100 kilometers. Just to put that into context, the International Space Station hovers around 330 to 410 kilometers above the surface of the Earth. Mount Everest, which lies in Nepal, is around 8,848 meters, which is roughly 9 kilometers. So you can actually make that comparison, okay? So almost 10 times the height of Mount Everest is the space. So we have different orbits in space. We have low Earth orbit called LEO, medium Earth orbit, MEO, and then we have the geostationary orbits, which is very far away. You could say about 36,000 kilometers away, okay? But primarily we'll be focusing today towards the LEO orbit because that's where NEPALISAT-1 was launched and deployed. When NEPALISAT-1 was sent to space, it actually was sent to International Space Station first, and then from there was deployed. And the orbit is a special orbit called International Space Station orbit. It has an inclination of 51.6 degrees and is roughly 380 kilometers. So you'll notice here it's 330 to 410 kilometers. And that's because it changes its orbit because sometimes there could be debris and it's always correcting its orbit as the time goes forward, okay? So since the satellite was deployed with the help of ISS, the orbit that NEPALISAT-1 is in is also in ISS orbit. So if you have to look at the space segments, you have a spaceport where you launch the rocket, and then you have the rocket itself, which takes something towards the space, and then you have spacecrafts, or more specifically, satellites that do some kind of mission for us, okay? So rockets are the means to reach them, and satellites are systems that helps us to achieve the missions that we want to achieve, all right? So today we'll be primarily focusing on satellites because that's where my expertise is in. If you think about space environment, it's very different from the environment that we live in Earth. And it's quite an interesting environment where we see a lot of radiation. And that's primarily because of the radiation that's coming on from the sun, okay? And these are high energy particles. And if you put a system in space, it has to sort of accept or be in that environment and still work and still function. And the engineering problem for us is to make sure that those kind of systems can work in such high energy particle environment. such as space. Okay, so one of the issues we see when we launch a spacecraft into orbits is the radiation problem. Another thing we see is a huge difference in temperatures. So I think space is around minus 270 degrees Celsius. So it's very cold. And that creates certain challenges for systems in space to work. Because in Earth, we have what is room temperature is about 25. We can see that in coldest parts of the Earth, we have around minus 50, minus 60 degrees. But in space, we have minus 270 degrees. However, what we do see is that satellites in low Earth orbits are facing roughly a degree difference of around 100 degrees. And what we have to do initially is to place them in these kind of chambers in a vacuum condition and then test the satellite and see whether it works or not before we send it up to space. So in space environment, one question is about radiation. Another question is about thermal vacuum. How do we deal with these constraints? Okay, so those are environments specifically to space. But then you also have rocket environment because you need rockets to send that system to space. We need rockets. And because of rockets, we have a lot of vibration that goes on, right? So let me change that to pointer. So what we see with rockets, these rockets, is that when they launch off, they vibrate. And that actually creates a problem for the payload or the system that is inside that rocket. And for that, we need to do all these kind of vibrational testing in y-axis, in z-axis, and x-axis. So that's x, y, and z, and see whether the satellites can survive such situations or not. We also have situations where we have to test shock because rockets are multiple stages. So when a single stage moves on to the second stage, and when a second stage moves on to the third stage, there is a pyrotechnic which allows it to separate. And when it separates, it creates a shock. And that shock actually is implied on to the payload. And that can create problems on the satellite itself. So not only do you have to design a system for space environment, but you have to make sure you design the system that can withstand rocket environment as well, okay? So let's move on to small satellites. And this small satellite is called a CubeSat. So NEPALISAT-1 is a 1U CubeSat. What does 1U mean? Okay, so if you have to really imagine a 1U CubeSat, it's roughly about the size of a Rubik cube, okay? And it's 10 by 10 by 10 centimeter in size. And these are standards for nanosatellites. And nanosatellites weigh between 1 to 10 kilograms. You know? They're very light and small, and they have shown that they have huge potential in doing a lot of different things, which we will explore today. So if you take 1 unit of CubeSat and then keep on stacking them, you can actually create a longer CubeSat, similar to how we stack bricks, and make more energy to create more interesting missions if that's needed, okay? So for a 1U CubeSat, 1 watt of energy that we actually use. So if we need more energy, we need to create a bigger system. What we do see is an exponential growth in small satellites, specifically on CubeSats. And these, as you'll notice here, in 1999, 2000, you saw a very small amount of small satellites being launched. Now we see an exponential growth. So we have a lot of these satellites being launched every year. And we predict that this will continue for some time on, okay? Kyushu Institute of Technology that I did my PhD on is ranked as the #1 institution in the world for the number of satellites launched. So we have all these different projects going on: OBA, Spatium, Horio4, Tenko. And as we discussed before, we need all these facilities to make sure that the satellite works, right? So we need to test. And it's a standard where we take a satellite and then we put them in these kind of thermal vacuum chambers and see whether these satellites work or not. So these mimic space environment, these kind of chambers. And then we have a shaker for rocket environment. We have also a shock shaker that mimics the rocket environment again, because as I said, when rockets separate, they create shock. We also have anechoic chambers like this to test satellite radio, because we are doing wireless communication. So we need to check whether the satellite can communicate or not. So all these testing allows us to understand whether the satellite will function in the future or not, okay? So all these are the satellites that have been tested in Kyushu Institute of Technology. And moving on with BIRDS-3, BIRDS-3 had 3 satellites. One satellite from Japan, which was Igusu, one from Sri Lanka called Ravana, and one from Nepal called NEPALISAT-1. All right. So we had 8 members, including 2 Nepalese. And as you will see here, Nepal was leading this project. Okay. The timeline for NEPALISAT-1, the 1U CubeSat that we built, we first proposed it to Ministry of Science and Technology on April 2017, and we actually were able to receive the payment for BIRDS-3 for NEPALISAT-1 in September 2018. It took 3 different governments to push the proposal forward, and now we have a satellite operational. The project timeline for NEPALISAT-1 is as follows. We began to design the satellite in October of 2017. We finished building the satellite in February of last year, and then we launched it in April 17. Deployment was done in June of 2019. And since then, we have operated the satellites. And these are some of the images we have received over a period of 1.5 years of operation. Okay. We also have been recognized worldwide for the work that we have done. As you'll notice, we received the 2017 awards and also the Better Satellite World Awards in 2019 for the work we have done. All right, so that's with the small satellites. And let's have a look at the satellite technology specifically for Nepal. We'll first explore disaster response. So in 2015, we had a massive earthquake. I think most of you had experienced that as well. And Wired reported that Nepal's earthquake was mapped in 48 hours. Okay, so it took 48 hours for the whole of Nepal to be mapped. And you will see a number of satellites being involved during the earthquake to map Nepal. We had Worldview, Digital Globe, Landsat 8. Landsat 8 is from NASA, and these are actually big satellites. So if, let's say, we have a disaster, and during the earthquake of 2015, we had that disaster, national and international organizations then can request UNOSAT to trigger the International Carters for space and major disasters. And that allows us to have access to free image data from all around the world. So you have all these government organizations and private companies giving free satellite data if you need them, okay? So if you notice here, this is a high resolution image of Kathmandu, and this is a slightly lower, still high resolution image. And the importance of smaller satellites is that now, because we have small satellites being launched in an exponential manner, we can now map the Earth, every position of the Earth every day. And that allowed us to map Nepal during the earthquake as well. So because of these kind of small satellites, we are able to now take images of Earth every single day of every point, okay? So that gives us quite a lot of data to work with. I think when you grow up and let's say you are in high school and in the future you take up university and from university you go on to master's degree, I hope that you will think about using machine learning, or as popularly people know as artificial intelligence, using codes or using algorithms such as support vector machines, deep learning models such as convolutional neural network, deep belief networks, and autoencoders. These can be used to separate. If you have an image, you can separate between what is a building, what is a vegetation, what are trees, and so on, okay? So in that case, if we can separate that, let's say in the future, what can happen is if there is a earthquake and we take a satellite image, we can then start, instead of humans counting number of tents, the artificial intelligence will automatically count number of tents for us in an image. And then with that, we can do rapid assessment. And with rapid assessment, we can do rapid response. If we know how many tents there are, we know how many people there are, and then we can allocate resources accordingly. So you'll notice that with availability of more and more satellites, we have more and more data. We can start training these kind of machine learning models, which will be, I think, interesting for anybody who's in high school at this moment. And then in the future, we can then apply these kind of machine learning models for rapid assessment during disasters. So one thing is to use remote sense data. Another is during disasters, we need to communicate, we need to talk, okay? If we can send some kind of voice message or text message to someone about our situation, we can get help. So QO100 amateur geostationary satellite. We talked about geostationary orbit before. These are orbits where the satellite appears to be stationary because it rotates at the same rate as the Earth, and it always faces towards the same direction all the time. What we can then do is transmit voice to that satellite. Then that satellite will relay that voice to somebody else. And this can be done with amateur radio equipments. So using geostationary satellites, if all communication are down, we can still communicate with other people. So that's possible. We can also send text. So these kind of messages can be sent to International Space Station if you have the right equipment. And then that text can be repeated over and over again until and unless somebody else has that kind of equipment, they can receive that kind of message. And if help is required, that person can send help. So not only voice for satellites, we can also use text messages, and we can send it up to satellites, and then the satellites can relay that information down. Okay, that's possible too. Another concept, and I will try to explain this in the most simplest way possible, is called store and forward. What we can do is we have some kind of sensor in Earth. That sensor is sent to the satellite. That satellite stores that information. That satellite then moves to another location, and then we can then downlink that sensor data. So through space, we're able to receive these kind of remote sensed data. Okay, so it could be water level, it could be temperature, whatever data that's required can be stored onto the satellite using a module called low powered long range module, LoRa. So do search this in the internet. It's quite popular in Internet of Things these days. And if you can use that in the future, I think it's going to be a game changer as well. So using these kind of modules, we see in the future that store and forward can be possible. So NEPALISAT-1, going back to NEPALISAT-1, we can see that these design aspects were employed when we were thinking about missions. So two things we saw during earthquake. One was that we needed to do some kind of remote sensing. We needed Earth data. Remote sensing is data that we take from space of Earth. Images of Earth are remote sense data. And then we need to communicate. That is, we need to talk from point A to point B. Okay. So for that, we implemented those first steps in NEPALISAT-1 as well. We have a store and forward system where if you want to put your name in the satellite, you can request that on our page and we can place your name on the satellite and the satellite will beacon the message to the Earth for 24 hours. We also have done demonstration of LoRa modules, and we have also taken images of Earth, which is the first steps towards remote sensing. So let's have a look at airborne tracking now. So now everybody is talking about COVID-19, right? The pandemic. And because of that, we need to find ways to deliver PPE, which is protective equipment, and also COVID-19 test samples effectively to different places. And that can be done by drones. Okay, so we can use drones to distribute or receive or deliver these PPE or COVID-19 test samples. But to track those drones, that's another question. So how do we track these drones properly? Turns out we can actually use satellites to track them. By placing these kind of transceivers, we can then control using our laptop. We tell the drones where to go using our laptop. It talks to the satellite. The satellite then talks to the drone, and then we can move the drone to any location we want. Okay, so that's also possible using satellites. Another thing you want to look into the future and you want to study about is ADS-B, Automatic Dependent Surveillance Broadcast. This is a new technology that helps us to track aircrafts. And in a place like Nepal, where a lot of accidents happen, tracking aircraft can be an important way for rapid response if accidents happen. Okay, so in these cases, what we see is that this kind of tracking is done by ground segments, by ground, but it's also possible to track these kind of planes by satellites. And by tracking them, we know exact location. And In a case of accidents, we can then track those plane if necessary and then retrieve them. So I think, especially in places like Nepal, satellites can play a key role for if there is any accidents that happens for spacecrafts. Okay, and that in the future, if we can extend it, probably we can extend it to road transport as well. Another interesting thing we want to see is urban and rural mapping by space systems. Recently, we heard that India was building a system. Let me check here, pointer. So India was building this road right in the disputed area of Nepali and India border, okay? So right in the center, they were building it. And you will notice that at certain point, this line becomes darker. So that's when India started building the road. And we can figure out exactly when such roads were built. So we can see that those roads were built in January 2019, and this kind of information can be retrieved using satellites. Okay. We can also observe whether construction work has been going on or not using satellite data. For instance, this is Pokhara Airport, Pokhara International Airport. You'll notice construction going on. If the government says it's 80% done, we can verify using satellite data whether these constructions are done for 80% or not. So that's a way to cross-check if that's necessary. Another thing we can do using satellite data is NDVI. And I want you to copy this and search it yourself in the future, NDVI. This is a very useful index, okay? This is a very useful index. And what we can do using NDVI is to see which part of Lalitpur, for example, this is an image of Lalitpur, we can see where the greenery are. It just shows us which part is green. You will notice that a lot of Lalitpur is urban area. There is very less greenery. Okay. And we can also, if we zoom in a little, figure out which area is more green. So that means more vegetation. And which one has less vegetation. So using satellite data, we have all these beautiful information that's coming out, which can be useful for urban planning, for Lalitpur to plan, let's say, if they want to expand parks, they can then figure out where to expand parks. And if they want to figure out how much greenery there is in that city, they can then calculate that as well using satellite data. Okay, so these are just practical examples of the use of satellites. I'm not sure if you have heard about Glacier Lake outburst flood, okay? But this is starting to become a common problem in Nepal. Because of global warming, glacier lakes, which used to be ice before, are slowly starting to become water. And because of the water, they are slowly expanding, as you will see here. In 1990, the lake was like this. And in 2015, the lake became this big, okay? So it has doubled in size. And this kind of information can be retrieved by using temporal satellite data. So if we collect satellite data from 1990 all the way to 2015, we can then observe the growth of these kind of satellites. So by using these kind of data, you'll notice it's growing. So at certain point, there'll come a point where this natural dam could break and all the water could flow down. Okay, so if all the water flows down, flash floods can happen and a lot of lives can be lost. And we can use satellite data to prevent such flash floods from happening if we monitor them properly. We can also use synthetic aperture radar, called SAR. These kind of images have problem because if there is cloud cover, we cannot see the lake. But with active sensors, we can actually penetrate through the clouds and then observe these kind of lakes, okay? And we can observe them growing or receding and make a decision on whether to conserve that lake or not. So this is directly related to Nepal's glacier lakes. And in the future, if you think about joining journalism, if you think about being a media personality, or if you think about writing for magazines or newspapers, what you can also think about is using satellite images to do investigative journalism. So that's also possible. And if you have learned Python, or if you learned how to use coding, you can access all these open source satellite data. Open source means it's openly available to everyone, freely available. And you can use this data to then make good judgments on size of the lake, what's happening with the lake, what's happening with the border disputes, what's happening in Lalitpur, what's happening in all of Nepal. And you can write these kind of articles by using satellite data. So this is still a possibility for the future if you're interested in journalism. Okay. Now let's have a look at internet. So it is truly a time to be excited for space, because as we saw before, what we saw before was that we saw an exponential growth in small satellites, and that trend is predicted to continue. We'll see not just constellations, we'll see mega constellations, because I just read in the news recently that China was launching 10,000 satellites in the near future. And it's quite an exciting time for anybody who's building satellites, okay? And what we see, the use of those systems are on internet, remote sensing. Remote sensing means taking images of Earth, and also tracking. Tracking, we talked about aircraft tracking. You can track ships, you can track anything using satellites. But what I want to focus here is on SpaceX, a company in US, a private company in US that has launched a constellation called Starlink, and they provide internet service. Today, you saw that my internet wasn't good in the beginning. I'm using Subisu, Nepal, and roughly the downlink speed is around 18.53 megabits per second, okay? But let's say I use Starlink satellites for internet. I would have roughly got, how many times is it? 5, then you have, that is around 3, so 8 times more, okay? Roughly 8 times more the speed from space for internet. So what we see in the future is that everybody will have an antenna, similar to how we have TV antennas at our home. and we'll be receiving internet from space rather than fiber optics, okay? Rather than ground systems, we'll be receiving internet from space. So that actually opens a whole lot of possibilities, especially in rural areas where they don't have access such as uh, such as how we are having here in Kathmandu, right? We have a lot of internet service providers that provide us internet like Subisu, WorldLink, but in village areas, we don't have that. So using these kind of satellites, we can provide electricity, internet, also electricity in a way that if you have a solar system, then you have electricity off grid, and then you have internet supporting that. That means the possibilities in that area is endless because now you have internet access, you have off-grid power systems, and now you can do whatever you want by learning and reading from internet. Okay, so that opens a whole new possibility for Nepal if we have access to internet from space. So let's have a look at how we can learn space technology in Nepal without spending a lot of money. Okay, space is expensive, sure. Like for example, launching NEPALISAT-1 cost us roughly 50 lakhs. Just launching a kilo into space cost us 50 lakhs. That's also pretty cheap compared to what it was 10 years ago. But still, that is expensive in context of Nepal. So let's see how we can cut down that cost, okay? So some of the challenges in Nepal we see is that we have a lot of challenges, but what we see is a funding issue. And we also see manufacturing base. We don't have proper manufacturing base. We also see that we don't have components available if you want to build something. And logistics is a problem. Logistics meaning if you order something from outside, the postal system doesn't deliver the products on time. Mobility is an issue because moving from one point to another is a problem. And we have a lot of bureaucracy involved in our government. So these are a lot of challenges that other countries have already solved, but are still an issue here in Nepal. Okay, so because you guys are the next generation, I think it's worth understanding these. So if you really think about first world countries, what they have done is they have created a government policy. And from government policy, they have created basic infrastructure. And then they have created a manufacturing base. And then comes in space education. And then slowly space technology. Okay. So that's how other countries were doing it. But for us, what we have done is done a top-down approach. Okay. Normally should have been a bottom-up approach, but what we're doing here is a top-down approach where we built a CubeSat first, and then we started pushing for a space education. Then we hope to push for a manufacturing base. We hope that basic infrastructure then will be built. And then hopefully in the near future, we have a space government policy. So that's where we're aiming at. So in that case, we looked at CubeSats. We should now look at space education. CanSats. CubeSats were basically satellites that looked like a cube. Now, CanSats are these kind of satellites that are built in a constraint of a Coca-Cola can or a can, any can. And these are non-flight satellites, okay? You don't send these to space. You use a amateur rocket, maybe, or you can throw it off from a building. But you just use or build these kind of systems to learn about the system, to learn about satellites, to learn about the whole project, to learn about embedded system, okay? So non-flight satellites are called CanSats, and they are primarily designed for educational purposes. And it's a very useful tool to prepare students and faculty for future CubeSat or satellite or space projects. Okay. So this has been a very effective tool, and I'll give you an example. So when I started to learn about space systems, I started with CanSats as well. That was in Korea. So I competed in the Korea CanSat competition in August 2014. And then I was certified as a CanSat trainer. We launched the first CanSat training at Kathmandu University in December of 2016. And so on. We have been doing CanSat training every year. And the idea is basically in such a way that I train somebody, then these people then train other people, and these people then go on to train the next generation. And every year we try to reach a younger generation. Okay. So for instance, I trained undergraduate students trained high school students. Then we want high school students to be training younger students to middle class students. And we also want these kind of programs to slowly move away from Kathmandu as well, because as you'll notice, it's highly centered in Kathmandu, where we had been doing these kind of trainings. And for the first time in 2020, we went out of Valley and we were able to train students with CanSats. And we hope that by learning CanSats from a very young age, you can then learn about these kind of systems. And by the time you reach my age, the possibilities are probably endless. Okay. And this is just an example of the CanSat training that we did in 2017 in the Institute of Engineering, which is Pulchok Engineering. And you'll notice that we have a laptop here, we have the CanSat, we throw the CanSat from the building and we communicate it wirelessly. And if you have done this, if you can show this and you can receive data and analyze it by doing this kind of simple things, you are able to then learn about space systems. Okay. And just quickly, what we see here is now we are trying to move everything to a simulated environment, so everybody has access to it. And our plan in the future is basically to have education. Right now we're doing space education, but we are also building space systems. And hopefully in the future, what we hope from you guys is that if you learn to build satellites, you will understand how to use satellite data. And hopefully, by using data science and machine learning, you can make an impact in the near future. With that, I would like to say thank you.
Am I audible? Thank you so much, Dr. Abhas Maskey, sir, for being informative and sharing valuable knowledge. I hope we all learn many things about the satellite and space technology. So now we are in Q&A session. If anyone has question to Abhas Maskey, sir, this is your time. You can write in chat box or even ask directly by unmuting yourself or by raising hand. Feel free to drop your question.
Hello. I have a question.
Sure.
So, see, being in Nepal, we have seen that we have only launched only one. We have only launched a satellite in the space, but we
Right.
have seen many other countries. Even like, for example, let's take our neighboring country, India.
Mhm.
there we have many companies like like the startup companies who are building
Mhm.
who are building small satellites, and
Mhm.
they are launching it to the space. So
Mhm.
and they are even building the satellite in a very very cheap price. So how
Mhm.
can we bring that thing in Nepal itself? Like how can we bring the cost down, and we can build satellite in our own country, inside our own countries?
Yeah, so thank you for the question. I think it's a very valid question where you're looking at, you're asking whether we can actually do space startups in Nepal. I think in many ways, if you think about India, India already has that infrastructure for a very long time, especially with ISRO, which is their, let's say, a NASA of India. And because of years and years of research, they're now spinning off into startup companies, and those startup companies are also building satellites. Um, in one answer is that the satellite cost has already gone down significantly because of commercial off-the-shelf components. But unfortunately, the cost hasn't gone down in such a way that Nepal can start investing. um, a lot of things, when you build a satellite and you launch it, the data has to make sense for the person investing. And in case of Nepal, especially, what we see here is that the data that's been available hasn't been utilized in the first place. Okay. So you build a startup and then you make a satellite and you launch it only when you feel that the data that's available isn't enough. So I would say it will take some time infrastructure wise for Nepal to start having its own startup and to start making business sense. Of course, you can use your own pocket money to build a satellite if you have enough money, but it has to, for it to be sustainable, for it to be year on, year out, it has to make a business sense. And what we see in case of Nepal, the basic infrastructure hasn't been built. Components, it's so difficult to get components. So those are policy-wise challenges and infrastructure-wise challenges that need to be solved first. And also, secondly, we have to make sure that all the data that's available openly is very simple data, even from Planet, hasn't been properly utilized. Trying to launch a satellite with our own money, maybe, especially with a startup. Government can invest so that the, let's say, human resource can develop. But for a startup to invest and make business sense, I think it will still take some time in case of
So
Nepal.
just a follow-up question,
Yeah,
like you
yeah,
mentioned
sure.
that the cost of the components are very high
Mm,
and even they're not available. But as I have been a part of many other startups, as a member or as a student in many of the startup companies in
mhm,
India as well as in Nepal,
mhm,
I have seen that they are making the components themselves. And like I'll take an example of a motor launching a rocket motor, which a small motor which costs around, let's say, $10 to $20, has been
mhm,
reduced to $1. They made it themselves. So I think the requirement is space education, like, so promoting space education and a proper space education, not because we don't have any curriculum in Nepal, so that students can learn the proper space education and their application. So how can we bring
mhm.
that further? And let's say about the startups, that how can we even launch rocket from Nepal, because as the international rules, rocket cannot be launched over any other countries.
Mm. So I'm definitely not discouraging for people to be building it here. That's not my intention. But you're right in a way that a lot of these new generation technologies, which are based on commercial off-the-shelf uh, devices or components, have drastically cut down the cost of, let's say, building a satellite or let's say a rocket or any space system. But I think you are talking in the sense of a breadboard. We call it a BOM. So it's bill of materials cost. Bill of material cost probably is $1 for sure. But I think what you will also have to think about is, even if you drastically are cutting down the cost of components, the issue has always been, or the bottleneck has always been on number one, testing. So you have to test it very well before you send it up to space. Anybody can build a satellite, it's not an issue, but it has to work. Can you make it work? I think that has been the challenge. A lot of people build satellites. One U CubeSat right now success rate is about 29% for educational satellites. Everybody's building it. It's just that it's not working. You can build it, you can cut down the cost, but can you guarantee that it can work in space? I think that's one challenge. Just talking about the challenge. And second
Sir,
bottleneck is, okay, sorry.
also please go on. I was about to ask another question to you.
Okay, second issue I see is we can cut down the cost of materials for sure. We can probably build a satellite for $1,000, for example, but the launching cost is still very high. And I think that will definitely go down over the years because of companies like Rocket Labs, which are specialized in low Earth orbit launches for small satellites. So um, eh, I think in the future, you're right in a way that it will make business sense if we invest in space education now, so that people can then learn how to build system and make it cheaper. But if in the other way, if rocket launches don't get cheaper, if newer technologies don't, if we put those satellites and then those cost of launching doesn't go down, that will be still an issue. And that's, I think, a bottleneck that I see, along with the challenge of making it work. Did I answer your question, Hriday?
Yes, sir, you answered my question. I have a very small last question about,
Okay,
so being sorry, I'm actually taking others time, but yeah.
sure, no
uh,
problem.
Sir, being a citizen of Nepal, we want a
Hmm.
our own space agency here in Nepal,
Hmm.
so that we actually can, bring the real experience, and we can really see a rocket being launched in front of our eyes, so that we can learn, we can motivate we can motivate the investors to invest on the startups, the space startups. So how can we, get ready? If, let's say, let's say the government, how can we as a citizen can go to the government to, build a space agency here? Because that's not easy for us, because there are no policies, there are no such, you know nothing's we can do. So is there any way?
So I think first is to get the government to invest in small amounts for space, right? So what we did for the first time in the history of Nepal was to allocate 1 crore 50 lakhs for space. That was the first time ever that the government used tax money to invest in space for CubeSat. So that was a first step. So now the next challenge is to get it investing a little more. So what we're trying to do, leverage right now, is to allocate funds for, let's say, some space-oriented programs. And if we can get the government investing every year and increase that investment as the years go by, I think we will see a point where we can have a space wing first, let's say in Nepal Academy of Science and Technology, which was the stakeholder for NEPALISAT-1. We can first start out by having a space wing that specializes in small satellites, in research for small satellites, that allows people like you to come build components, make it cheaper. Same thing we talked about. It's possible. It doesn't necessarily have to be a private company. And then if the space wing then, that experimental space wing then does well, and we have, let's say, NEPALISAT-2, who knows? If we can do that, I think we can then start leveraging that. We have now leverage power over the government to say, hey, now since we proved that we can actually build the satellites here, why don't we move from a space wing to a space agency? So what I see with a lot of other countries, so this is something that I studied, okay? So what I see with other countries is that they invest huge amount of taxpayers' money in space agencies, but the return of investment is very low, okay? And a lot of those resources are being in waste. And Nepal is not in a situation to waste taxpayers' money, because you already saw how much of our taxpayers' money is not being utilized. So imagine if we form an organization that wastes money again. That doesn't make sense. So I think it's important that we start out small, we start out slow, and as we slowly build up the capacity, we then have the leverage in the future to then say, hey, we need a space agency. So I would say it's not really necessary to have a space agency to start building satellites. We are already doing that. And hopefully in the future, we can leverage that and encourage students like you to actually join us and work in the future. Does that answer your question, Hidray?
Yes, sir. The answer was wonderful. I would like to
Mhm.
have your email ID, please.
Sure. I think Dipti can forward that email to you.
Thank you, sir.
Yeah,
So I have a question.
sure, Prabhat.
So there is a company called Blue Origin, Jeff Bezos company, which is helping others and helping themselves to. Um, Basically, I heard Jeff Bezos talking in an interview saying that they want to help other people inspired to start a space agencies from their dorm room, like Mark Zuckerberg started his Facebook. I mean, but how is it possible that even a huge space agency can start from a small room? I mean, it's hard to
Yeah, so
understand. And the next,
that's okay. So that's the beauty of new space. So we have entered a time of new space, and if we looked at Planet Lab, which I showed you, let me just show you quickly that picture. So if you look at this particular CubeSat, which is a 3U CubeSat, can you see that, Prabhat? Can you see this kind of this satellite? Did you see it?
yes, sir.
Okay, so that actually started from a garage and now has about 150 satellites in orbit and is providing 5-meter resolution of data, and it's taking images every single day. And that started out with a garage. Okay, so I would say if a private company started with a garage and then ended up building 150 satellites, constellations, right, using commercial off-the-shelf components. If a private company can do that, I think government has the resources to build or to start a space program from a garage and then move into a space agency. I think it's possible. So what you're looking right now here, and I think we were talking this, we were discussing this in Rome this year in a conference, CubeSat conference. And it's an exciting time to live because we have entered an age of constellations. Things are starting to get cheaper and space is getting more accessible to everybody. And that also means that if you start something from your garage, hopefully it can become something big in the future. That also means the government, if governments invest, I'm sure it can become a space agency. Does that answer your question?
Yes, yes, sir. And the next question I have that what is the
Okay.
physics behind that Elon Musk's SpaceX company? I mean, launching a spacecraft from ocean. I mean, from the middle of ocean. What is the physics behind that?
I think that's something that we are exploring here as well. What we are trying, what the idea is, so we have only limited amount of land, right? And imagine ocean covers a lot of area. So it makes business sense that it makes business sense to launch from ocean, and you don't have to carry those rockets. Ships can pull those kind of rockets easily, so you save a lot of money with that. Carrying takes it does, yeah. It's, I would say it's cheaper to move something on land, on water than land. So all these kind of, it makes all these business sense rather than science sense. I would say they're looking more towards the profits rather than science. Now what they saw was, okay, if we launch from ocean, it looks like it will cut down our cost significantly. Now, can we actually make that happen? I think that's where the direction is. Not like, oh, science, it's possible. Let's make it happen. It's more like business sense is possible. Let's make the science happen. I think that's just my opinion.
Thank you, sir. And the last question, I mean, it's not really the question. I just want to be clear about, is it really the rumor that China is about to launch the artificial moon? I mean, I've been listening to this rumor a lot.
Yeah, that's something that we have been listening as well. It's hard to say because what I did was I tried to study the first 1,000 satellites that have been launched, 1,000 small satellites. Okay, so I did a study, and all of the satellites that were launched from China had no information. So it's really hard to get information about satellites that have already been launched from China. So imagine things they're planning to launch, it's very hard to get access to. So somebody might have just announced it that China was making a moon, artificial moon, whatever, but it's very hard to verify that because we don't have access to those information. So if it's a rumor, it's possibly a rumor, but with China, you never know. I mean, I think impossible is nothing is something that they are moving forward with.
Thank you, sir.
We have one question in our chat box from Abhishek Karna. He said that is aerospace possible after undergraduate in physics?
Yeah, I think, of course, physics is the base. And what we see is, I can only say with satellites, especially if you have done physics and mathematics, we need a lot of people who have done physics and mathematics for attitude control, how the satellites rotate, because a lot of mathematics and physics are involved in there. You have to understand orbital mechanics. You have to understand the physics of orbits. You have to understand the physics of how the satellite interacts with its environment when it rotates. And that's something I think requires a lot of depth and knowledge in physics. And if you want to move into aerospace, if you have a background in physics, it's not an issue. I will just tell you that my background was mechanical and aerospace, but we never actually worked a lot with PCB designs and electrical systems. And when I had to go into masters, I had to relearn all these things. So I would say, even if, another example would be, we had from Bhutan, we had people, civil engineers coming and building satellites. Okay. So I think that's the worst case scenario, where we had civil engineers coming and building Bhutan-1, which was their first satellite. So if that's possible, I think if you have learned physics, pure physics, I think you can come in, you have the base, and now you can either do space research for spacecraft interactions. You can also do spacecraft charging. You can do attitude control. You can do orbital mechanics. So I think the possibilities are there.
Okay, the next question is from Resam Thakur. He said, the temperature of the side facing the sun is over 100 degree and the shadow side is below 100 degree. Then how is the condition managed to keep the satellite functioning?
Okay, so if you look at that way, right? If you look from a theoretical perspective, from a layman's perspective, it looks like that. Okay, it looks like there's this massive difference in sun's to shadow facing. But what we have seen is that the satellite's temperature rises up to NEPALISAT-1 temperature has risen up to maybe 70 degrees panel during sunlight. So it's it's rotating. So it's rotating. So you have some certain parts face towards the sun, and then it's very temporary, and then you have another facing the sun already. So it's not always pointed towards the earth. Okay, so that's one thing to note. And the
And
the temperature.
his,
Sorry.
yes, his question is how the satellite functions below the 0 degree.
Okay, below 0 degrees. So let's say from the sun, it moves into eclipse because in a ISS orbit, you have 90 minutes of one orbit, okay? And you have 60 minutes in sunlight and 30 minutes in eclipse. In 30 minutes, it does go below 0 degrees, okay? So the panels reach about minus 40 degrees. We have also seen the batteries going down to -5. But what we do is we test them here in Earth up to -10 degrees for batteries. Battery is tucked inside, very deep inside the satellite. That's the worst case where scenario where if the battery reaches about -10 degrees, that's something that we really designed for and can accept, can actually still function. So what happens is that the satellite goes into eclipse. We see a steady decrease in temperature. The panel reaches -40, but the battery goes below zero, goes to 5 degrees, and then -5 degrees, but then it doesn't go below that. And by the time that happens, it moves back to the sunlight area. So it goes up again. So what we see is worst case -5 degrees and the batteries are still functioning, which is the worst case. Batteries you have to really protect. Panels can be -40, batteries cannot be -40. That's a big issue, okay? Uh, so the satellites are still functioning in that case. And if you're designing something, if you're designing a satellite, whatever you're designing, you have to design it according to the orbits that you're going to release in. And you know what the orbits are going to impose on your satellites. You know that it's going to go, let's say, -5, -10 degrees, but you need to test that on the ground, make sure that it works before you send it up to space. Does that answer your question?
And how those in the geocentric orbits manage it?
Yeah, so geocentric orbits are interesting orbits because one thing to note is that it's moving as it's along with the Earth. Okay, so it has a 24-hour rotation. So every 24 hours is one orbit, right? So in that way, what we see is that they have thermal regulations being done. Inside, they have protective layers, they have active thermal protection, they even have heaters. So in NEPALISAT-1, what we have done, and I hadn't told you this before, we actually have a chamber for battery box. We have a chamber for battery, and inside that chamber, we have put heaters. So in worst case, it goes below certain temperature, the heaters turn on, okay? And it heats up the battery. So I'm thinking for geostationary orbits or the satellites that are released in geostationary orbits have, number one, active thermal control. They have systems that have active heaters to heat them up if it's necessary. And also in 24 hours of orbits, we also have sunlight, and it goes back to sunlight from eclipse. So it's not, I don't think it's such an issue. So for geostationary orbits, they have, it's a 1 ton, more than a ton satellites. They have their own systems, especially thermal control systems built in to control that. For CubeSats, we don't have such thermal control systems.
May I ask one question?
Sure.
Excuse me. I want to continue.
Okay, sorry.
Uh, what I actually knew is in the sunlight, the face that is facing the sunlight is over 100 degrees, and the face that is facing away from the sunlight is below 0 degrees. And in this condition, how they manage it?
One thing they do is they use thermodynamics. What they do is they, even if you measure the temperature, it's not really 0 degrees. Maybe the ambient is zero, but what they do is they have a thermal channeling from one area that is hot. They channel it to the cold area. And because of the laws of thermodynamics, it allows that heat to be transferred towards the cold area. Okay. So it's temporarily 100, sure. But then that temporary 100 is, that heat is being transferred to the other panels. Now, one important thing to understand is that the outside temperature is 100 and 0 degrees, but the inside temperature is actually in a better situation than that, because the panels are in the worst case scenario, and those are designed to withstand that kind of temperatures, okay? And that allows the inside system to be functioning. What you should be worried is inside. If the inside temperature is about minus 30 degrees, now you have a big issue. But if the panels are 100 and another one is 0, you're still okay in the terms that the solar panels have to withstand that. But besides that, if the core system is still working, I don't think that's an issue. Okay. Number one, again, to repeat, one, they have thermal regulation in a way that from that hot temperature surface, that is being channeled to the colder surface because of thermodynamics. It's simple thermodynamics, because you have conduction. You can use metals just between the panels, and that metal can transfer that heat to the cold part. Number one. Number two is, you have to ask yourself, that 100 degrees, that 0 degrees, is it inside temperature or the panel temperature? If you're talking about panel temperature, that's not an issue. It can withstand it. If it's an inside temperature, if an onboard computer is 100 degrees, that's a big issue because it shuts down. If it's 0 degrees, it's still possible. But if it's minus 40, minus 50, then that's a problem. Did I answer your question?
Yes, sir.
Okay.
Sir,
And
I have a
another
question related to the microgravity.
Sure.
So yes, the first question would like to be how the International Space Station, there is a microgravity there, or how the artificial gravity is there.
So I don't think they have created any artificial gravity there. Um, so, oh, you see astronauts doing weird stuff in ISS. Those are all the experiments that have been doing in microgravity environment. They have
Yes,
not
sir.
created artificial gravity at all. Sorry, did can you can you say something? You wanted to say
No, sir.
something?
No, 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 no. I was just saying
Okay.
yes, sir. I was responding to it.
Okay, yeah. So, so I think to create, if you have seen, let's say, Martian, for example, Martian is a really good movie. And if you've seen Martian, what they do is they have a spacecraft that goes to Mars, and that creates an artificial gravity by rotating. Okay, but you have to understand the physics behind it. But ISS itself is not created to have an artificial Gravity, it's created to do microgravity experiments and whatever, for example, if you want to grow plants in microgravity, you take it up to ISS. If you want to do some kind of microgravity experiments, you take it to ISS. So the existence of ISS, as far as I know, is this kind of laboratory to do microgravity experiments. That means to create artificial gravity doesn't make much sense in that case.
So I have second question related to the
Sure.
shape of Earth.
Okay.
I had a picture which I got when I was researching. So I'll
Mhm.
just share that. So this is what I had seen as the real shape of Earth
Mhm.
according to
Mhm.
Google. First of
Mhm.
all, is this correct?
Mhm. Mhm.
Yes.
So I would say it's not. We have from a young age we have actually seen Earth to be round and pebble-like and all this cleanly circular object, but it's actually true that it's not as ideal as we have been thinking. I cannot verify if this is incorrect or correct, but what I can say is it's definitely not round as we have thought about it. It's definitely not smooth. It's very, very rocky. It's very, uh, yeah. So if you have to start taking,
So we
if you have a
assume
surface,
this
yeah.
we assume this as being
Uh-huh.
the uh, approximate shape of the Earth. Then we
Mm-hmm.
have issue in this side, the purple side, when there's a satellite. So the
Uh-huh.
satellite
Uh-huh.
is rotating, so this part
Yeah.
will be
Yeah.
unstable,
Yeah.
including
So
even this part.
yeah, so what we've seen is when designing of orbits, we use ideal cases, but we also think about worst case scenarios. For example, because of the shape of these, let's say Earth, and because of some conditions, we might have, I'm not sure because of the shape of the Earth or not, but we have this thing called South Atlantic anomaly in low Earth orbit. Okay. So that's where a lot of highly charged radiation particles exist. And that's the only area where those particles are highly concentrated in those radiation particles. And that creates a lot of issues for us because we have designed the satellites not to withstand that kind of radiation. So that's an acceptable risk that we take sometimes. That's just an example that I'm trying to say. Not everything is designed to withstand, especially for university satellites or for, let's say, low Earth orbit satellites. What we have done is we have taken worst case scenarios, but there could be even worst case scenarios such as South Atlantic anomalies that have high amount of charged particles that could then create this thing called single event latch-ups, single event events, and then that could actually create the satellite to reset or to function abnormally. But then um, we design it for worst case situations. But if case situation does happen, we have some kind of mechanisms to reboot the satellite so that it comes into original state. So if it goes through South Atlantic anomaly, and for some probability it actually comes across highly charged particles, we then have the satellite functioning abnormally, but then we can reset it so that when it goes to another position, it functions properly. But it's all about probability, I think. It's a acceptable risk. And um, in in similar way, if the Earth is not exactly circular or round as we have thought about it, uh, those kind of systems could probably think you can think that as acceptable risks if it goes through those area and has problems. You see what I mean?
I apologize, but the question was a little bit different. I
Okay.
actually meant as this
Which part
part.
can you see?
Just a minute, I'll just turn on the spotlight.
Okay.
This part
Uh-huh.
and this part. So let's say
Okay.
satellite is here. So it tends to move to this side because this part is little bit stable and round.
Mhm.
Similarly, here the part is little bit round, so this part is being an unstable part, or you can say the satellite does not
Mhm.
get stable
Mhm.
here.
Mhm. Mhm.
We
Mhm.
know this. We know the magnets, the electromagnets are used sometimes to stable the satellite. So,
Uh-huh.
but if it is a geostationary satellite which is
Mhm.
orbiting around this part of the world, how
Okay.
that satellite stays stable forever, like for most of its time, not ever, most of
What
its
the geostationary satellites are very far away from the Earth. So I would say 36,000 kilometers. You can imagine 36,000 kilometers is quite far away. So I would say it has more problems from the sun rather than the Earth. That's number one. And it has active attitude controls. It has a lot of thrusters. It's not like a CubeSat where we don't have a lot of attitude control. CubeSat do have, for example, I think you can make a case for CubeSats because you could be right in a way that because of the structure of the Earth, the magnetic field could be different. That means the way it interacts with the CubeSat could be different because we have, let's say, a magnetotorquer, which is passive, and it's a magnet. It's a solid magnet that we put sometimes, and that allows us to control the satellite. I think you're right in a way that it creates an instability for low Earth orbits, which especially for small satellites, I think, yeah, that could be true. But for bigger satellites, which are very far away from the Earth, I think the major issue would be when we design something for geosynchronous orbits, we are more concerned about radiation and problems from the sun rather than the problems from the Earth. Does that answer your question?
yes, sir. Thank you so much.
Okay. Yep.
Yeah, we have the one raised hand from the service of Kata, so you can unmute yourself and ask the question. Sabin Sapkota.
Dipti, I think there are some questions from the chat. I think you can start reading them. Maybe.
I have a question.
Okay.
My question is that how can you access the data of NEPALISAT-1 by us?
Mm, mm. Um, so right now we have not publicly released the data. Um, if you have a amateur radio license and if you have a amateur radio equipment, you can receive the CW signals. The CW signals have data in it. It has temperature data, it has current data, it has voltage data. So that is open. CW is just Morse code, and that's been beaconed always, okay, every time, all the time. So that's something that you can receive and analyze if you want to. We can help you with that. It's not an issue. I think we should have a software built for that as well. So if you go to our website, probably you can find it there. If it's not there, you can always email anyone from BIRDS-3, especially, I think we have an email there. You can email them and get some help with the CW analysis. But there's another data. It's not just CW that's coming out. We have AX25 packet data that we use for uplink and downlink, and that is not distributed outside purely because of research purposes. Um, The images that we receive and downlink are done through AX25 packets. And that is, if once we create those images, we then publish it online on BIRDS-3 website. But besides that, the core missions data, I don't think you have access to that, but the bus system data, which we call like a voltage or current or system data, can be received through the CW. So if you want that kind of information, do send an email and they will send you a software that help you to analyze that CW data itself. But you need to have at least access to CW somehow, either by amateur radio license or by requesting those kind of CW information. Did I answer your question?
Yes, sir.
Yeah,
Okay.
and we have a next question from the Rohan Acharya. He said, so as you talk about the Starlink and many satellite launch every day, what can be the negative aspect of it? Due to high quantity of satellite in orbit, there is
Yeah.
a high chance of space debris. Big form, more and more. What can you do to reduce it?
So
So I have a
one
question
problem.
relating to.
Yeah. Yeah. Sure.
Sorry,
Please.
sir, to interrupt. I have a question. Recently, Elon Musk said that he is going to launch a spacecraft which will collect space junks. So how it is possible? I mean, there's a lot of satellites doing the work, and there is a lot of work going around there. So how is it possible to cancel all those, gravity kind of thing and fly into the space and be able to collect all those space junks?
Okay. So let me try to answer both of that question together. So what we've seen is because of all these satellites, we'll see thousands of more satellites in the coming years. That means we will have a lot of debris. Debris is when those satellites, some of the satellites might not work. As I said, especially with 1U CubeSats, you see for educational institutions, we only see 29% of those satellites working. So rest of the 71% don't work. And those are all debris, okay? So with Starlink, what we see is one issue is debris problem, that is for sure. But before we launch those satellites, we have to show, we have to prove JAXA or NASA or whatever organizations that we are linked up with. In Japan, NEPALISAT-1 was linked with JAXA, which is the NASA of Japan, right? So they check all the documents and we have to prove that our satellites will deorbit in 25 years, within 25 years. If we, if they see that it does not deorbit in 25 years, they don't allow us to launch the satellites. So all the satellites that are being launched at this moment in time have to fulfill that debris requirement, okay? So that allows us to know that at least if the satellite doesn't work, it has to go down in 25 years. Our satellites go down in 2 years in low Earth orbit in about 380 kilometer. So it's not an issue in case of, let's say, Nepal, NEPALISAT-1, that the debris will be there. But in case of Starlinks, all those satellites that are being launched have to fulfill that requirement. Debris requirement is there, and those have to be fulfilled, and that's on. They can only launch it if that's done. Okay, so that's one. Second issue, what we see is because of Starlink's, they have this really weird design which reflects the light of the sun. Okay, so it reflects the sun's light towards Earth. And what we have seen is light pollution at night because of Starlink's satellites, okay? Because those lights are being reflected towards Earth, those are creating light pollution in the night sky. So that's something they are actively working on to reduce. So imagine thousands of those satellites. Every satellite you can see in the night sky would be a problem for us. Now, for anybody who's interested in astronomy, in astrophotography, that would be a pollution because that's noise, right? So in case of what Elon Musk says and what Elon Musk does, you have to be really careful, because if you have read his book, if you have read his not autobiography, if you have read his biography, one thing to note down is that he always overestimates the work, and then it gets done maybe 10, 20, 30 years on. It will get done someday, but if he says it will get done in 2020, it's probably likely that it will get done in 2030. Okay, so that's something to note for Elon Musk. But when he says that he's going to clean up the space junk, I think there has been serious research right now, um, to mitigate debris in large scale. And right now, I don't have a specific answer on how that's possible, because it's still an active research. But down the years, in 2030, we are talking about space traffic, like how we talk about air traffic now in Earth. We will be talking about space traffic in 2030. So that's really an issue. And a lot of companies, not just SpaceX and not just Elon Musk, but a lot of companies, a lot of startups are building these systems that allows us to clean the debris in space. Okay, those are active research going on. Some are rendezvous, where they actually go and grab the satellites and then help them to deorbit. Some are using nets. Some have special materials that grow from the satellites, and then they allow it to capture those debris. So all these new technologies are coming forward, but at this point, it's very difficult to say who's going to do who, and if really Elon Musk is really going to do it. But I would say it's an active research, and things are moving forward in case of debris. And even in case of Nepal, we are actually trying to move forward with debris monitoring, because I think Nepal is in a lower latitude. It's good enough latitude, and we have higher altitudes for monitoring such debris. And I think if we have the right investments, probably in the future, we can have some kind of debris monitoring system in Nepal as well. So does that answer your questions, I think?
Yes, sir.
Okay,
Yeah,
thanks.
we have question from the Sovin Sapkota. What are the business objectives of SpaceX in cooperation with NASA?
Okay, so as far as I know, SpaceX is a contractor. That's how they are getting the money. SpaceX is a contractor for NASA. That means NASA says do this and SpaceX does that. So one of the example is NASA needs to send astronauts to International Space Station. SpaceX takes those people to International Space Station. NASA needs to do some kind of refueling mission. Refueling meaning needs to send let's say food or equipments to International Space Station. Then SpaceX basically is the cargo guy. It's almost like DHL. You imagine DHL or postal service for space. SpaceX is basically doing that for NASA. I think that's the relationship right now, the
And,
the main relationship.
and due to very limited time, we will take one more question. Sorry for the time restriction. You can ask the question on our Facebook page, and you will get we will get back to you as soon as possible. And we have the feedback link, so you can give the feedback. Uh, it's in the chat box.
I have one question.
Hi, Rachel.
How can you participate in this CanSat training programs?
Yeah, so we'll right now, every year we were doing those CanSats in CanSat programs in Brihaspati School. right around the time of, let's say, Dashain holidays. We were doing that every year, but because of the pandemic, the situation, it's very difficult for everybody to come to one place and work. So I think what we are trying to do now is to move everything to a simulated environment that allows you to just have a laptop and internet and then actually learn CanSat systems. So if we can take everything, it's an active research, but if we can move everything to simulated environment, I'll let you know. But if we do if we actually conduct a actual CanSat training program in the future, uh, I think I will send an email to everybody. I think I can just let Dipti know about it, and Dipti can send information to everyone. And if you're interested, I'll be more than happy to help you out. And I think if you are especially with high school or middle school students, I think that's the target area that we are trying to reach out to. So we want more younger kids to take up CanSats, more younger kids to be taking space education. So we have a better working force in the next 10 years.
Thank you, sir. We will be more than happy to participate in this training
Okay.
programs.
Yeah, thanks.
Thank you once again, Dr. Abhas Maskey, for joining us, and we will be organizing such informative session and competition in coming days also. So keep in touch. And finally, I would like to request all of you to fill out the feedback form. The link is in the chat box, and you can write 3 words to describe today's session. And for this question, you can write on our Facebook page, and we'll reach out to this Abhas Maskey shirt, and we'll very soon we'll answer your all the question. Thank you.
Okay. All right. Thank you very much, Dipti, for organizing this. Should we stop the presentation or everything now? The discussion?
Yes.
Okay. All right. Thank you very
And
much.
thank you, Sher, for joining us.
Yeah. Yeah. No
And
problem.
thanks to all for joining us and making our session very interactive and interesting too. And and I just want to say that AEN believed for the exploring together. So I would like to request you all, let's join together and explore and learn together. So thank you everyone for joining us.